Okay, we are looking good. Alright, hello everyone, welcome back to our math library. It has been a little bit, I actually don't know how long it's been, but it has been a while since we've looked at this library. We're actually going to be starting a little new section of the library where we look at some equation parsing. So we're going to be looking through the reverse Polish notation. What that means, it's practically postfix notation. And then we'll also be looking through the Shunting-Yard algorithm. And then from that we will be looking at how to evaluate equations, and then from there we could be looking at creating something of a command line interface for our library, which would be pretty cool. And who knows from there. So yeah, today I just wanted to give an overview of the Shunting-Yard algorithm, and then we'll look through an example. And then after that, we will look through some of the template code that I have and that I prepared for the library. It's just the reason why I'm not going to be typing this out is just because it's very monotonous and it doesn't really provide any educational value. It's just, these are mainly just going to be utility functions, but all of the actual algorithmic code I will be coding live. So that will be next time. But for now, we're just going to look through Shunting-Yard algorithm, and then we'll look through the code after that. Alright, so the purpose of the Shunting-Yard algorithm is to parse something called infix notation. So when you've seen an equation like this, this is called infix notation because it's written as a human would read it, so in order. And our goal now is to actually make it so that a computer can evaluate it, because this isn't too helpful for a computer because it doesn't know much about precedence. So if a computer were to evaluate this left to right, it wouldn't do that. Well, I mean, here I think it would, just because it happens to be in this notation where left to right is proper. But if I were to do something like a 1 plus here, it would not evaluate it properly, because it would do the 1 plus the 3 raised to the -2 times 27, and it would just evaluate it left to right, rather than evaluating it based on precedence of certain operators. So it's going to be, we're going to have two lists here. We're going to have a queue and a stack to kind of keep track of which elements go where, and then the output will just be the queue at the end, which we will look at. All right, so let's start with the algorithm here. So the first part of the algorithm, I don't have it written down here, but is going to be to essentially parse some tokens. So that was one of the tricky things that I struggled with last time we did this, because this was a challenge, I think, at some point. And the parser that I created was not perfect. It wasn't close to perfect. But I have fixed up the parser, and I do have some some good code that we will look at next time. But the first part is going to be to parse this infix notation expression into tokens that the computer can look at. So this essentially in tokens would be a sign, then an open parenthesis, 3, the exponent, -2, multiplication, 27, division, 4, multiplication, pi, closed parenthesis, plus, and then a 1. So this will be the first step, to actually put it into just to parse the tokens out of the string. So taking this and putting it into a list here. And then essentially this loop is just based on all these tokens. So this loop will just iterate through all the tokens here. So we start with reading the token, like I said, and identifying the type. So each token will have a type. The sign will be a function. This will be a left parenthesis. The 3 will be a constant. The exponent will be both a function and an operator, where operator is a subtype of a function, so on and so forth. -2 is still a constant. The pi is also a constant, but we will represent that differently. So then we want to do a few things, based on what type it is. So if it's a number, we're just going to push it to the queue. And we will see why this works in the example here. So if it's a number, you push it to the queue. If it's a function, you push it to the operator stack. Now, the relation between functions and operators is, as I said, operators are subtypes of functions. However, when we're evaluating based on precedence, functions can be considered to have 0 precedence, because the parentheses will be what determines the precedence here, not the function itself. So if it's a function, we just push it to the operator stack, simple as that. And then if it's an operator, now we do need to consider precedence. So while there's a function at the top of the queue, or at the top of the, I believe this might need to be stack. I'm just gonna, I will leave it like that for now, but that could be wrong. So let me actually just check on this real quick. So the condition here is, okay, so the first condition is going to be, or the larger condition will be this whole thing, and with the operator at the top cannot be a left parenthesis. So I mean, that kind of makes sense because the parentheses have more precedence than an operator, so you don't want to pop something from the stack when it has greater precedence than the current token. And then for this condition right here, the second half of the condition, it's going to be that there is a function that is not an operator at the top of the queue. So that is, this is actually correct here. So there's a function that cannot be an operator at the top of the queue, or there is an operator at the top of the queue, or at the top of the stack. This is actually stack, actually. Yeah, so the function is at the top of the stack, or an operator is at the top of the stack with greater precedence, or the operator at the top has the same precedence and is left associative. So left associative essentially just means that it is associative, so that the associative law applies to that. So this will be with functions like multiplication, division, just multiplication, addition, subtraction, but not the exponent, because it's not the same the other way around. So yeah, that's this condition here, and then that's all ANDed with the operator cannot be a left parenthesis. And in that case, we're going to pop operators from the stack to the queue. So we essentially just want to take everything, we want to keep going from the stack all over to the queue when those conditions are met. Now if the token is a left parenthesis, we can simply just push it to the stack as if it were a function with some precedence. If it's a right parenthesis, now we want to pop until we find the matching left parenthesis. So if you've taken a comp sci class, when you probably learned about stacks, you most likely would have learned about how stacks can be used to evaluate. They can be used to evaluate parentheses expressions. So you can evaluate the validity of a parentheses expression just to make sure everything is balanced. So say, for example, we had something like that, and that, I don't think this is balanced, but you could use a stack and keep pushing open parentheses onto the stack, and then you would pop from the stack every time you found a closing parenthesis. So we're essentially going to do the same thing, except this time we have stuff in between the parentheses. So we want to pop everything from the stack to the queue until we find a left parenthesis. All right, so those are all the possibilities, and then once we're done with the loop, we want to just pop all the operators from the stack to the queue, just to finish out all the stuff, and then we end up with the expression in reverse Polish notation or postfix notation. All right, so let's go through an example and we will see more in detail about how this works. All right, this is not big enough, I don't think. How do I want to do this? All right, I will just leave it like this for now. Or I can also just zoom in. I can also make this smaller. Okay, there we go. That works. All right, so we will start just by going through the tokens. So as we separated them in the token parser, so sign is a function, so you push it to the stack. So the stack has sign now. Left parenthesis, push it to the stack. And so we're representing the stack as the leftmost element being on top. In a list, it would be the other way, where the last element would be, or the top of the stack would be the last element. We have a number or a constant, so we push it to the queue. So 3 is put in there. We have an operator, and there is a left parenthesis at the top of the stack, so this while loop never runs once. It does not run at all, so we just push it to this top of the stack. -2, push it to the top of the stack, or push it to the queue. Then with the multiplication sign, this is an operator. However, this loop will run once because the exponent sign has higher precedence than the multiplication sign. So we're going to pop the exponent sign to the queue. So we get a 3, -2, and then with the exponent sign, you may see a pattern here. This kind of matches that just in postfix notation. And then we push the multiplication sign to the stack. 27, constant, put it in the queue. Division, we have an operator here. There's an operator at the top of the stack. The multiplication sign has equal precedence and is left associative. So this condition passes. So then we pop the multiplication sign from the stack, put it onto the queue, and then push the division sign onto the stack. Alright, next is a 4, constant, add it to the queue. Simple as that. Then the multiplication sign, once again, the top of the stack is a division sign that has equal precedence and is left associative. So we pop from the stack and put the division sign on the queue. And then we have a left parenthesis next, so we cannot run the loop again. And then after that, we are done here. So we push the operator onto the stack. Then we get a constant pi, add it to the queue right here. Now for the right parenthesis, we want to push to the queue until we get a left parenthesis. So we start with this is our initial stack. So we pop the multiplication sign, put it in the queue, and then we get to a left parenthesis. We're going to pop the left parenthesis, but we are not going to push it to the queue. And we're just going to discard it. We'll free the memory or whatever. So the stack is now just a sign function. Alright, then we have a plus sign, so this is an operator. The top of the stack is a function here, which is not an operator. So we're going to pop it from the stack to the queue. So we get a sign in the queue, and then push the addition sign to the stack here. Have a constant added to the queue, and then we're done pretty much because we've gone through all the tokens. And then at the end, we want to push everything from the stack to the queue. So this is what we end up with in the end. So let's take a look at this, because like I said, this is going to be our reverse Polish notation. So let me increase the size a bit. Alright, so I will leave that there for half a second. Okay, let's take a look at this this reverse Polish notation, and we will see how this actually helps us. And I will also grab the initial expression up here. There we go. So this is going to be infix. Let me just expand this a bit. And this is postfix / reverse Polish notation. Just like that. So we can already see a bunch of the similarities here. So let's start by looking at this. So the similarities here, okay, well, we can start by looking, I mean, this 3, 2, and the exponent sign is almost identical to the infix notation, except that the negative, or the exponent sign rather, has been pulled out to the back. So maybe we see that we want to have a 3, -2 linked by an exponent sign. And now this is why the postfix notation, or the postfix term, comes into play, because this is essentially going to be, we're going to link these two, and now you should start thinking about trees and stuff, about linking two nodes, or two elements, two tokens. We're going to be linking the 3 and the 2 with the exponent sign. So this can kind of maybe look a little bit like this, where we have a 3 and a -2, something like that. And then this could evaluate to 3 to the -2. So there's that. Now if we consider this as one token, let's call this a token A, then we now have A 27 times 4 division pi multiplication sign 1 and a plus. So once again, this pattern kind of arises where we now have this kind of, alright, so let me highlight this here, because this became A. So this whole thing right here became A. But now we see the same pattern arise where A times 27 becomes A 27 with the multiplication sign at the back. So we're going to kind of continue doing this pattern where we merge two nodes, or where we link two nodes using an operator or some function until we get to the end. And this kind of, and because of the way that because of the conditions that we use to push onto the stack, push to the queue, pop from the stack, and so on, this will be in order of precedence. So I mean, we can also just kind of see how this works in our infix. So if we start with sign with the if we start with the original expression, so it's sign there divided by 4 times pi, like that, plus 1. We start with the exponent, so then it becomes a sign times 1/9 times 27 times 1/4, or I'll just say 27 divided by 4 times a pi and plus 1. And then we evaluate these two now. So sine of 3/4 times pi plus 1. Then we evaluate this. Sine 3 pi over 4 plus 1. And then we evaluate this now. So sine of 3 pi over 4 is root 2 over, or is 1 over root 2 plus 1, and then we are left with these expressions here, or this expression here. So this is our final expression, which is 1.707, I believe, something. So yeah, this mirrors that process essentially of taking the postfix notation and evaluating it just by merging nodes or linking nodes. So we now have A27 linked by a multiplication. So we have we can call this B is equal to 27 times A. So then our stack, or our stack is, or not our stack, but our list of tokens has been reduced to a B, a 4 division pi times sine 1 and then a plus. And then once again we have a B and a 4 and a division. So C is equal to B divided by 4. So then we have a C, a pi, times sine 1 plus. Keep going. D is equal to C times pi. So then we have a D, a sine 1 plus. Now this is different because we don't have an operator linking this sine and the D. However, the sine is something what we call a unary function. So we have a unary function, which is a function that will only take in one argument, as opposed to a binary function, which takes in 2 arguments. So binary function will be something like plus, because plus takes in 2 addends. Multiplication takes in two factors. Division takes in a divisor and a dividend. And subtraction takes in two arguments as well. So this sign in D just becomes E, which is equal to the sine of D. So we're still following that same pattern of evaluating from left to right, but we're linking some nodes using an operator, except this time we're only linking one node to itself. So the evaluation will be like that. So E is equal to sine D. Then our stack is reduced, or our list is reduced to E, 1, and then plus. And then our final answer, F, is equal to E plus 1, which is exactly what we have here. So essentially, we're doing the same exact thing, just in a way that a computer can understand it, because there's no way a computer can look at this and be like, all right, let's do this shit. Let's start here, because it doesn't know until we parse it into a queue. So this is how that works. And as I said before, we should start to think about this like a tree. So in our code, once we have our reverse Polish notation, which we obtained using a stack and a queue, which are familiar computer science concepts, we're going to kind of create a tree out of this expression here. Right? Because we're just evaluating it and it'll look, and the evaluation will turn out just to be a tree traversal, which is pretty cool. So let me bring this over here, or over here, and I will copy this once again, and then we will build the tree now, as opposed to just evaluating it by hand. Alright, so let's start. So we start with our 3, -2, then the exponent sign. So the operator becomes a node, our root essentially, and then we push, and then we link two children, the 3 and the -2, using this exponent sign. So the exponent sign is the node, or is the root node, and then that has two children. So we will call this root A. So as before, our queue becomes A 27 times 4 divided by pi times sine 1 plus. And then the same thing. So A27, and we link it using a multiplication sign. So this is now the root is equal to B. So then we have a B, 4, division, dot, dot, dot. So as before, we have our division as the root, B and 4 are the children. So now we have C as the root. And then we will do C pi times, so C and pi linked together by a multiplication. And this root is now called D. And then we have our D sine 1 plus. And then, as I said before, sine is a unary function, so we only need to have one child for the sine node, because the sine is still the operator that's going to be linking one node, or that will be the evaluation of for one node essentially. So we get a sine D, and that's all. So this new root becomes E, and then we have E, oops, no, what happened there? E 1 plus, so they're linked together by addition, E 1, and this new root is F, and then now that we only have one element here, we can just return f. Now let's backtrack. Let's look at what f is, so we can kind of see what this entire tree should look like. And all I'm going to do is I'm going to start with f as the root, and then I will just backtrack. And I will substitute in the past roots. So we start with f. But f is just the plus of e and 1. Now we substitute even further and get to this. So then we get a plus that links a sign that evaluates with d here. And then a 1. We can keep going. So we have a plus as the root node, sign of d, but what is d? It's just this node over here. So it links to a multiplication node, and that links to a c and a pi. And then we have the 1 at the end again. Now we need to substitute for c, so we get a plus. Let me actually make this a little smaller, but so I'll just start at the bottom with c. So the b and the 4 are linked by division, like so, and then this is linked to the multiplication with the pi, and then dot dot dot. And then we need to substitute for b. So we have a, 4 linked together by multiplication, which is linked together up above by the division with, or this should be a and 27, sorry. And this is the division with 4. And then we just keep going to the root. So then we have a 3, -2, linked by an exponent, linked by a multiplication with the 27, dot dot dot. So now if we look at the whole tree, this is going to be a little annoying to do, but I will figure it out. Okay, so we'll start with the root, the main root, which is the addition. So you can see that this will always be the addition here, or the top root, because it is the last set of nodes that we link together. So we start with the addition. That's our main root, and then we go to e, and then we go down to 1 and e. Once again, e becomes the plus of 1 and sine of d, but d is the multiplication of pi and c, and c is the division with 4 and b, but b is now the multiplication of 27 and a, where a is the exponent of -2 and 3. So we get this really disgusting tree, but that's just because I chose a crappy example here where this all looked like that. But either way, if this is our final tree, let me just drag this down here and zoom in on it. So this is our final tree, and from this tree we can then evaluate this expression as many times as we want, and we essentially just go to the bottom and evaluate upwards, backtrack as we did. So we'll start with the 3 and -2. So 3 to the -2 evaluates to a 3 to the -2. This multiplied by 27 gives us a 9. Or wait, gives us a 3, sorry. A 3 divided by 4 gives us a 3 over 4. 3 over 4 times pi gives us 3 pi over 4. Sine of 3 pi over 4 gives us a 1 over root 2. And apparently I wrote +1 twice. Okay, that's fine. And then we just add. So then we get the result, 1 over root 2 plus 1. And that's it. That's the final answer right there. So that looks good. That is essentially how this tree will work out. Yeah, so that's Shunting-Yard and the evaluation after Shunting-Yard. So yeah, that's the algorithmic introduction to this, of this video here. And now we're going to take a look at some of the code that I have prepared for, that I just want to introduce to you guys, but we don't need to code it just because it's pretty monotonous. Alright, so we'll start with some of the library code that I have, and these were all coded live. So the string stream, the dynamic array, and the AVL trees, these were all code programmed live in programming challenges before. So if you want to look at how these all work, then just go ahead and watch those videos. I hate the self-promotion, but I don't want to just give you guys some code and not explain it. So that's these classes right here, or these files. And then for the other files that I have pertaining to Shunting-Yard directly, what is up? Clip Studio Paint X tutorials, okay. Sorry, god damn it. Yeah, so this file here, syfunctions.h, is just a header file containing a bunch of callbacks for functions like cosecant, secant, cotangent, arccosecant. No, I'm not shitting on your name, don't worry about it. I was just... don't worry about it. I'm sorry about that. Yeah, so there's the arccosecant, arcsecant, arccotangent, and the absolute value, addition, subtraction, multiplication, and division. Now we need these functions here just because we need a callback to something that will allow us to add two numbers together, two doubles. And then there's a minimum function and a maximum function too. So those are the callbacks. Now as for the other two files, there's going to be an syutil.h and an syutil.c. So in the header file, we start with some includes here, just the string stream and the AVL. We will need those for arguments. Then we have our macros, and then we have our macros for the just the definition here. And then we also have definitions for two types. So the first one's going to be a Boolean, which we have seen before, where false is just a 0 and true is just a not 0. And we are using a type def here to convert a character to a Boolean. And then we also will type def a character into something called a token type, because we will need, as I said was very important, is the type of the token. So in token parsing, we need to classify each token as an operator, as a function, as a left parenthesis, as a constant, as a whatever, and these are all defined right here, and we just use a character to we use a character to store that. Oh, you're in 9th grade, that's cool. It's good that you're starting early though. Yeah, this math here, I mean, 9th grade is early, I'd say. That's, if you're talking about like the OpenGL stuff, then yeah, that's completely understandable because there is a lot of linear algebra in there. But there's also a lot of algorithmic stuff in here, but that's cool that you're starting earlier. It's good that you're starting early. But yeah, back to this. We have our macros here that define the types of tokens that we'll have. So operator, constant, constant string, which will be for stuff like pi and the natural base. Functions, left parenthesis, right parenthesis, and else, just as an error type. Then we will have two callbacks here. So we will type def a function callback to a unary function evaluation, which will take in one argument, and then for the binary function evaluation, which will take two arguments. And now we can see why these functions will be helpful, because we need to kind of pass a pointer to some function, and these functions will do just that. We can just pass in a reference to divide, and then when we call evaluate, whichever function that may be, it will be, it will just call this function using the 2 parameters that we give it, which will be cool. And you can probably guess now that these functions will be stored, or these callbacks will be stored in a tree node, where we look at this. So when we call evaluate, we just have a function callback attached to the tree node, which we can then just call and evaluate based on the arguments that we give it, which will be cool. All right, next we have a few structures. I will start with the token structure, which is this one here. So we simply store a type and then a union. So this is kind of similar to the JSON stuff, where we have a type to specify which value in the union we are currently using. So we have a double for a constant value, a character for a string value. This is just, I mainly have this for debugging purposes. There isn't too much use for it in the actual algorithm. I just had this when I was building up the code and testing it, just to make sure everything worked out. And then we also have 2 structures, a function and a constant, which we will look at right now. So these structures will serve as a wrapper for functions and constants. So for the functions, we have the type of the function. The type of the function, which will be a function or an operator. Or actually, this was not supposed to be included. Well, we just have a name for the function. It'll just be a string, and then we have a state. Now the state, since this character is pretty big, it has 8 bits in it, and we can store 4 things within that 1 bit, within that 1 byte. We can leverage bitwise operators to look at the individual bits here. Some of the math stuff I learned in school, but most of the other code I learned on my own, kind of like what you're doing right now, which is cool. Just because there's a lot online in comparison to what school offers in most cases. But yeah, so this state will have 5 bits to store the precedence, which as we know is going to be super important with these conditions here. And then we have the 5th bit, which represents if it's a function or an operator. And we know this is already a function. We just want to specify if it's an operator or not, because this is just the function structure. Then bit 6 will be if the function is left associative. Like I said, that's going to be for the conditions as well. And then bit 7, the last bit, will be if the function is unary or binary, and this will affect how we evaluate it based on the number of arguments that we want to pass in. And that will also serve as a specification for which union value we are currently using. So if bit 7 is 1, then we want to call the unary function evaluation callback here. And otherwise, it's going to be bit 7 will be 0. So we want to use the binary function evaluation callback there. Yes, I do know how to use Python. If you're looking to get into programming, Python is a very good starting point, because it's pretty simple. Looks almost exactly like English, which is cool. Yeah, and then for the constant, it's just a name and a value. And just the name will be pi. Once again, the names in the functions and constants don't need to be there. I just have them there just for debugging and printing purposes. All right, then we have our token structure, which takes those together, as we talked about before. And then now we're going to be looking at some of the last structure, which will be used in the tree. So this is going to be the token node, which will, like I said, have an attached token to it. So when we call evaluate, we can just look. So if we call evaluate on, say, this node right here, on the sign node, we can simply look at the attached token, which will be a function, and that function has an attached callback to a unary function, which will just be sign. So we can use sign there as the evaluation, and then since we are representing this as a binary tree, we need to have pointers to the left and right the left and right children of this node, like this. OpenCV, I do not know much about that. I was thinking maybe something about it, but I'm kind of focusing on OpenGL right now. But that could be that could be an idea, because OpenCV and OpenGL are kind of similar, but not really. But maybe at some point. Yeah. Alright, so we have our binary tree node there. Maybe you've seen that before. And then we have a bunch of utility functions, which I will go over now in the source file here. So in syutil.c, we have our includes here, string and standard lib, a standard library. The first four functions are going to be to get to parse the state variable in the function state of the function state. So we have get precedence. Get precedence, like I said, takes the first 6 bits of the state. So all we have to do there, or the first 5 bits rather, sorry. So all we have to do there is take a bitwise mask. That's what this is here. This bitwise mask where the last 5 bits are activated. So when we bitwise AND it with the state, it will just return whatever the first 5 bits are. Because if you bitwise anything with AND, or if you bitwise AND a function or some value with 1, you will just get the original value. I do not have a streaming schedule at all. I just do whenever I have shit prepared. Yeah, it's just whenever times work for me. To be honest, there's no. I typically try to release 3 videos every 2 weeks or so, which has been my schedule for a little bit now. But there's no, I don't have any days where I need to stream on. Alright, so that's precedence. Then the is function. We're just going to take the bitwise mask of the 6th bit, and we return a boolean, and the boolean will be true if the value is not 0. So if this bitwise AND results to the 6th bit, which it may, then it will return true. With left associative, it's the same thing, just using the 7th bit, and then unary will be the 8th bit, using the same principles. Alright, next is going to be character is number, and that's simply going to return true if the character is either a digit, a decimal point, or a negative sign. And then we have a bunch of constructors for the tokens. This will be, you can pass in a type for the token. Then you can also pass in certain values based on whatever you want to create. So for example, sy create token constant, you will pass in a double value. This will call create token passing in the corresponding type, which is constant, and then it just sets the double value in the union and returns that value there. And then we have create token constant string, same thing, create token unary. This, once again, these 3 right here, create token unary, create token binary, and create token operator, were all for debugging, where I just wanted to set the string value to the function that I set it to, just so we can get to print it out just to make sure everything works. Then we have left parenthesis, which just has a left parenthesis in the string value. Right parenthesis, same thing. Then we have free token, which will just free the pointer, which is right here, which is cool. Then we have create a default function. And this is not, okay, yeah. This is, I'm going to be there's a few errors in here, but I'm going to be updating it with the correct code in a bit. So there's a create default function, which will actually populate the function structure in the union here. So this will actually set values in here. So the state, we by default the state will be it'll be unary and left associative, so that's by default, and also an operator. I think that's what it says. Yeah. Okay. Then we set the union evaluation to null, just so we don't actually have anything stored there. Then for create default unary function, do the same thing, except we pass in the type, pass in default parameters. Evaluation is what we pass in here to the call of the function, and then we call create unary function, which is over here, and we will pass in the evaluation. The type will be function, the precedence will be 0, and left associative is true. And then we do this something similar where we create a unary token, set the type, set the name of the function, then we determine the state, which is the left state, or the left associative state will be just left. If it's left, then we want to get a 1 in the 6th bit. Then for the type, if it's a function, we want to get a 1 in the 5th bit. And then for the state, we're going to pass in a 1 in the 8th or in the 7th bit because it is unary. And then we just bitwise OR all of these together. So we bitwise OR the 8th bit active with the left, so the 6th bit maybe, or sorry, the 7th bit is always active because this is unary. And then we bitwise OR that with the 6th bit, which may be active or not, the 5th bit, which may be active or not, and then precedence, which we clear out the last 3 bits so it doesn't interfere with the state. Set the type, set the union evaluation callback to whatever we pass in. And then something similar with the binary function, where we do the same bitwise OR stuff there, except the 7th bit will now be deactivated since it is binary, and that is the corresponding value in the state here. Alright, and then we have a create node function, which we will just pass in the reference to a token, and we're just essentially allocating a binary tree node with some value, which is a reference, and then set the children to null. For free node, it's essentially a post order traversal where we free the children first, call the same method recursively, free the children, and then free the current node. For free node deep, I don't think this function is ever called, but we just free the token as well. And then the last two functions here are evaluate unary and evaluate binary. And these are just easy functions so that we don't have to go through all these accessors or all these values. We just simply go into the token pointer, get the unary function, and then pass in the double X here, and then the same thing for binary, except we're passing in an X and a Y. Alright, yeah, so that is pretty much the Shunting-Yard algorithm introduction and the introduction to the code that we will be using when we actually write this algorithm, which will be next time. But yeah, this was... Yeah, I'm still working on a few memory things. The algorithm I have right now is a vast improvement on when we last wrote it, because last time we did the Shunting-Yard algorithm, it was the token parser was very inaccurate in many instances and corner cases. So I improved it, and I made it more accurate and more general, which is cool. So we will be looking at that next time. And yeah, that's all I have for you guys today. Do I know machine learning? I don't think I do. I don't. I know what it is, but I don't know. I actually don't know how to program machine learning. I might I'm not sure if I'm going to get into that at some point, but I probably should. I probably will, but not right now. I got a lot of other work to do. Machine learning is not at the top of my list, unfortunately. But that should not stop you from learning about it, because there's an absolute fuck ton of resources on the internet about it. Excuse my French, but yeah, you should definitely look into that if you want. But yeah, apart from that, this is all I have for you guys today. Just I will be putting this code on the GitHub repository. Take a look through it if you want. You don't have to, but if you just want to familiarize yourself with some of these functions that we'll be using in more depth, run some tests on it, then yeah, this will be on the GitHub in, I don't know how long, but I just need to clean up some of this code here, and then I will probably put it up there. So yeah, that's all I have for you guys today. Hope you enjoyed. Hope you may have learned something, maybe not, or you may have found this boring, which is probably at least the coding part, or overviewing the code is probably boring. But anyway, next time we will be doing something much more interesting, which will be actually programming the Shunting-Yard algorithm. Yeah, that's all I have for you guys today, and I will see you guys next time. Have a good one.